In the past decade, unmanned aerial vehicles have grown into a well-established field of robotics with many robust platforms and control algorithms. However, UAVs in industry are predominantly piloted by operators on the ground and exhibit very limited levels of autonomy. In contrast, fully autonomous flight has been achieved in research, and the degree of autonomy continues to grow. This confidence gap can be attributed to the robustness of control algorithms. Academic research focuses on proof-of-concept demonstrations with little consideration to adverse weather or sensor integration. To address this issue, the Drexel Autonomous Systems Lab has created SISTR, the Sensor Integrated Systems Test Rig. SISTR is a hardware-in-the-loop testing environment that can be utilized to test UAVs without risking the aircraft in flight tests. A 6 degree of freedom gantry encloses a mock urban environment. Sensor packages can be mounted to SISTR's end effector and the data fed back to a computer running the control algorithms. Using the aircraft's mathematical model, the response is calculated. The resulting motions are played on the gantry. Adverse environmental conditions such as varied lighting, rain, fog, and smoke can be introduced in a controlled, repeatable fashion. This provides a common test ground for benchmarking UAV sensor suites and control code. SISTR has been demonstrated with the representative UAV mission and sensor suite, landing zone identification using a scanning laser rangefinder. Code was created to read terrain measurements using a SICK LMS 200. Using established algorithms for mapping and landing zone ID, the helicopter was able to identify a clear spot to land. The algorithms were tested and refined inside SISTR. After developing this code, the sensor was then characterized for its performance in smoke. These environmental tests showed that the sensor could penetrate thin smoke but was blinded by thick smoke. This knowledge was instrumental in flight testing, where laser data of smoke and sparse vegetation look very similar. To expand the utility of SISTR, it was necessary to increase the operational area. Rather than build a larger gantry, the environment was scaled down. Scaling down the environment raises obvious questions, such as how will aircraft dynamics scale and how will sensors scale. To address these concerns, the system was tested using a representative mission and sensor suite. Vision sensors are common to many UAVs, and visual servoing is a building block for many other autonomous tasks. Code was created to visually servo a helicopter towards a window. This code was tested inside the scaled environment. The results from scaled tests are promising, suggesting that scaled tests do accurately approximate real-world flights. To verify these results, the same code will be flown on an autonomous helicopter. This will provide a basis to compare scaled flights versus real-world flights. The results of this work will provide a common environment in which UAVs can be benchmarked in controlled, repeatable conditions.